Okay, so now we'll be introducing and proving a very important theorem in representation theory called Schur's lemma. So what is Schur's lemma? Schur's lemma. So we're going to let A be a K algebra. Let M and be two simple A modules. Then an A module homomorphism M to N is either the zero map or an isomorphism. And this has another special case. So we'll have this more general case, A. And then we have B if K is algebraically closed. Then any isomorphism of simple modules is equal to some constant lambda times identity for some lambda in the algebra. So let's call F our putative homomorphism. So let F be a homomorphism from M, so I guess proof. So let F be a homomorphism from M to N. Now, what is the idea? So first we'll say how we're going to try to prove this. So we're going to have to use the fact that we have a homomorphism and the fact that our modules are simple. So when I have a homomorphism, we proved very earlier on two special kinds of structures that we have given homomorphism. Remember, we have the kernel of the homomorphism and the image of the homomorphism. And we also have the third thing. So we have the kernel, the image, and the fact that our modules are simple. And we're going to have to use those in our proof somehow. So, idea. So look at the kernel of F and the image of F since these are submodules. It's always good to look at the structures you have, and since we have homomorphism, we have these structures for free. We already proved that these are submodules. So we know something extra though. We know something extra. M and N are simple A modules. And now you can already see the idea forming. Because if the kernel of F is a submodule, it's going to have to be in M. If the image of F is a submodule, it's going to have to be in N. But running into a problem, we're stating that A is a simple module. And that is in fact how we're going to go about proving our lemma. So we look at the image for now of the homomorphism. We already know that this must be contained in N. But N is simple. So either F is equal to 0, or if F is not equal to 0, the image of F has to equal N. There is no in between. If it's some subspace in N, then N was not simple to begin with. So it has to be that the image of F is equal to N. Also, the kernel of F is contained in M. Again, M is simple. So either the kernel of F is equal to M, and this means that F is equal to 0, right? And then that's not interesting because F equals to 0, so let's suppose F is not equal to 0. So suppose F is not equal to 0. Then this implies that the kernel of F is trivial. Now, if the kernel of F is trivial, which means that the 0 element in M goes to the 0 element in N, and we have a homomorphism. This means that we have, in fact, a bijection. So we have a bijection, which implies that F is an isomorphism. Okay, so that proves our lemma. And the key thing that we used was that given our module homomorphism, this came for free with 2 submodules, but we were dealing with simple modules, and therefore that places restrictions on what F can be. And in fact, the restrictions are so strong that we either have the 0 map or F is in fact an isomorphism. Now the second part, so let me erase this, B. So we're going to let F be an isomorphism. Okay, so again, the trick is that we're going to look at a space that comes for free. Now, in this case, the space that comes for free is a kernel, the kernel of something. So we already know that the kernel of f is trivial. So we can't directly work with f. We're going to have to we're going to have to massage f in such a way that we can say something interesting about the kernel of some operator. We need to make that kernel much more interesting. So I suggest that we look at the kernel of this map. So look at kernel of f minus, and this f minus constant times an identity which acts on m. So first note, f minus lambda times identity is also a homomorphism. Why? So we have a homomorphism, we have the endomorphism acting on our module, and remember we have to prove that, so we already have f being a homomorphism, and therefore we have this to be the case. Okay? Because f is a module homomorphism. So we prove now that our special operator is a homomorphism. One, f is, of course, a linear operator, and so we have the following to be true. And so f is a homomorphism, so we know that the first term becomes that, and then we have this. And then the script, the capital script, or EA, the endomorphism, is a linear thing, and so we have this to be true, which acts on M. Okay, and we have obeyed our condition. So now we're going to have to look at the kernel of, so look at kernel of f minus lambda times identity. Now I claim that the kernel of this map is all of M. This is M. Why? So why? Well, a proper eigenspace of our map can't exist. Because remember, M is a simple module. So if it can't exist, this implies that in fact A minus lambda is 0, since the eigenspace is all of M, and therefore this means that F is equal to lambda times the identity. Okay, and this ends our proof. So we'll end this video by a definition. A module is semi-simple if it is a direct sum of simple modules. Alright, and this ends the video.